Hey guys, and we're back. Video 2, day 2. Alright, so let's talk about how to determine these rate laws of these mechanisms. Okay, so we're going to start with a mechanism in which the first step is the slow step. Now, why? Because that's the easiest. Okay, so we're going to start with the easiest example, and then we'll get to the slightly more complex one. Okay, now, carbon monoxide appears as a reactant in this balanced chemical equation. How do we know that this has to be a mechanism? Because if I predicted the rate law for this, I would predict rate equals K times the concentration of NO2 times the concentration of CO. But instead, CO doesn't appear at all and NO2 is squared. So we know this has to be a mechanism. So here is the mechanism. Okay, so I'm going to show you the mechanism. There you go. And I have colored one blue. The blue one is the slow step. Okay, blue for cold and ice. That's about as clever as I can get here. All right, so the first step is slow, the second step is fast. Now, we're assuming that these steps are elementary steps, which is why their rate laws can be easily written. If we look at the equation, if this is an elementary reaction, it's rate equals K times the concentration of NO2 times the concentration of NO2. Since these are the same thing, you could just combine them and say NO2 squared. All right, the rate law for this one, rate equals K times NO3 times CO, which is exactly what we see over here. Now, do you already recognize something? I hope you do, and that is that these two are exactly the same. The blue and the red rate laws are exactly the same. And doesn't that make sense? Because what did we say before? The slow step is the one determining the overall rate. And if the slow step comes first, who cares about what comes after that? Right? That's what's slowing you down. Once you get past the first step, the rest of it is irrelevant. So the rate is completely dependent upon this first step, this first slow step. What does this look like from like a mechanism, like a line perspective? Okay, so here we go. We're coming from reactants, we're going up in energy. Here's our activation energy to our first sort of transition state where our sort of activated complex is. Now we're gaining some energy back, but we've got a second step, hit another transition state where we have some sort of an activated complex, and now we're going down in energy again. Now overall, we started here, we ended here. Overall, this is an exothermic reaction. There were two steps that had activation energies, but in each step is gonna have an activation energy. But what do you notice? The first step is way bigger, right? So this is the rate determining step, and this is sort of a pictorial example of what you saw on the previous slide. So let me go back. So what's the simplest way I can tell this to you? If the first step is the slow step, whatever the rate law is for that step, that's the rate law of the overall, which you see proof of that here. Okay? So easy one first. If the slow step is the first step, the rate law of the slow step is the rate law of the overall mechanism. Done. But what if the slow step is not the first step? Okay, now we've already talked about how this is a termolecular process, and guess what? It does actually match the observed rate law, but I'm telling you, you should know that termolecular is rare. So even though it does match, this is a process, and you would always be provided this information, so don't worry about that. You're always going to be provided what these steps are. Now in this case, you see that the blue step is the second step. And neither one of these rate laws matches the observed rate law. So clearly there's some more stuff going on here. It's definitely a little bit more complex. All right. You also notice that you have a weird looking arrow here. This is an equilibrium arrow. What that means is that this can proceed in the forward direction, or that can proceed in the reverse direction. So what that means is that nitrogen monoxide can react with bromine, diatomic bromine, to make NOBr2, but then that's the fast step, right? And then next up comes the slow step. Well, what happens is you get this huge buildup of NOBr2, And once you hit a certain point, it's like, man, screw this, I'm not being used, I'm going to decompose. And it'll decompose into the reactants it came from. So this step moves in this direction. It also moves in this direction. Okay? And they're both fast steps because this is the slow step. All right? Now, but here's the trick. And the next slide explains this, but I'm not really going to go into that with you guys because that's something I would go into more with Chem 2 than Chem 1. But what I want you to do is this. This is the rate law of the slow step, correct? And the slow step should determine the overall. But take a look at this mechanism. Is there an intermediate present in the mechanism? Give you a few seconds to look, then I'll give you the answer. Yes, NOBr2, produced and then consumed. So that is an intermediate. An intermediate does not appear in the overall balanced chemical equation. Thus, it cannot appear in the observed rate law. But look what's here in the rate law of the slow, an intermediate. So we can't have that, right? But what I want you to do now is put your hand on the screen and I want you to cover up NOBr2 with your finger. So everybody put your hand to the screen and cover up NOBr2 with your finger. So I'm going to try to scribble it out with my mouse if I can get it to work. Okay, so cover this up. I'm going to keep scribbling. I know this is obnoxious, but I'm going to keep scribbling. So don't look here. Don't look here. If you add together everything else from these rate laws, what do you get? Rate equals K. It's the same thing, so you just say it once. Times, again, we're not looking here, not looking here, not looking here. NO times Br2 times NO. Another way to say NO times NO is NO squared times Br2. So what do you notice? If the second step is the slow step, use your thumb to cover up the intermediate, and the rate law should be everything else from both steps. Okay, like I said, that's proven here in the math. Okay, because basically you have to do a substitution. What we're doing is we're doing a substitution for the intermediate because the intermediate can't be there. And we know that the intermediate is equal to the concentration of NO times the concentration of Br2. So that's why the shortcut I said works, because NOBr2 is equal to the other two concentrations. It's a substitution. But like I said, I don't expect you to repeat any of this that you're seeing on this slide, on slide 68. It's just the explanation. All right. Okay, so let's do some practice. All right, so here we have a multi-step mechanism. So the decomposition of nitrous oxide, N2O, is believed to occur by a two-step mechanism. And there's the mechanism, and I'm telling you which one is slow and which one is fast. I will always give you the mechanism, and I will always tell you which one is slow and fast. Okay, so do not worry about that. All right, first things first, let's write the overall reaction. What do we not include in an overall reaction? Pause for effect. The intermediate. Okay, what's the intermediate? Monatomic oxygen. This guy, right? Produced and then consumed. All right, so we add everything else together then. We got 2 moles of N2O decompose into 2 moles of nitrogen and 1 mole of diatomic oxygen. Okay, now what is the rate law for the overall reaction? What determines the rate of a reaction? The slow step, right? And in this case, the slow step is coming first. So we don't have to worry about the fast step. It's relevant to us. So whatever the rate law you would predict for the slow step, which is the first step, that has to be the rate law for the overall. And what we would predict for that slow step is rate equals K times N2O, concentration of N2O. So whenever you go to determine a rate law for a mechanism, take your hand and cover up the balanced chemical equation for the overall reaction, because the mechanism has nothing to do with that. Or sorry, the rate law has nothing to do with the first answer. So the first answer that you provided on the slide, Yes, the rate law defines that, but if you look at that, it's going to confuse you. Don't look at it. Do not look at your equation for the overall reaction. Cover it up. Only look at the independent steps when you're trying to determine your rate law. All right. Okay, what happens if the first step is fast and the second step is slow? What was our trick? We're going to take our thumb and we're going to cover up our intermediate. Our intermediate in this case is N2O2. If we cover that up and we write a rate law that includes everything else. So rate equals K times the concentration of NO squared times the concentration of Br2, which is exactly what you see on the bottom right hand of the slide. The true answer to this question that you see in the PowerPoint, don't worry about this. I'm not going to expect you to write it this weird way with all the intermediate K's. Okay, you can just write it as lowercase k. That's fine. You don't have to write it as that weird fractional thing. Okay, look at the right of the answer block. Okay, K times NO squared times Br2, that's fine. All right, so this is fine right here. But remember to say, put the word rate. So rate equals, and then skip all the way over here, K times the concentration of NO squared times Br2 squared. Or Br2, sorry, not squared. All right, so that's it for this video. We only have one more video to do for today, and then you guys are going to have an additional assignment, okay? All right, so I'll see you in the last video.